Hello, today I will present a work of Michael Wade, Dan Safrir, and mine on a different way of handling the Meltdown vulnerability than the common one. So let's start with a question that some of you might ask. What is Meltdown? Meltdown is a speculative execution side channel vulnerability that affects various CPUs and can leak privileged data. Presumably, this definition is not needed for those of you who know Meltdown, and it is insufficient for those of you who don't know Meltdown. So let's go through a short animation to understand what are speculative execution side channels and how they can be used to leak data. As you know, CPUs try to execute instructions as fast as possible, and for that matter, they can execute instructions out of order. Applications are not allowed to access privileged data, which the operating system protects through the page tables. If an application tries to do so at some point, the CPU should trigger an exception. Yet this exception is not triggered immediately, as the CPU needs first to complete the executions of instructions that preceded the faulty instruction. While the exception is pending, many of Intel CPUs continue to execute instructions speculatively. The results of the speculatively executed instructions would be discarded and not committed to memory or visible registers. So presumably, everything should be fine. However, the instructions that were executed speculatively create a side channel. They impact the CPU caches, and their exact impact might depend on secret data that the user should not know. A malicious user can set code that would affect the caches based on the secret data that was read speculatively. Then, by timing accesses to different cache lines, the user can infer the secret data. Meltdown affects Intel CPUs and certain ARM CPUs and is mostly considered as a bug that should have not occurred. To recap, in Meltdown, the CPU continues speculative execution over access to privileged data, which is supposed to be protected by the paging mechanism. As a result, the CPU eventually triggers a page fault exception, but the speculative execution that have visible side effects, specifically on caches, can be used to leak the data. To further understand the implications of Meltdown, consider the common address space layout of a process as shown here. The bottom part of the area holds the user space application code and data, and the top part holds the kernel space, including the kernel code and data. This means that kernel data can be leaked to a malicious application that exploits the Meltdown vulnerability. To make matters much worse, some kernels, like Linux, hold in each process address space mappings to the entire physical memory. So any data that resides in physical memory might be compromised. The existing software solution is called page table isolation, or PTI. In this solution, each process address space, as reflected in the page tables, is split into two address spaces, one for the user and one for the kernel. And a trampoline is set in the address spaces to switch between the two. The only data that might leak in this case is the one that resides on the trampoline. While this scheme is secure, there is one problem with this solution: performance overhead, which is mostly caused by switching between the two address space, switching which is required for every system call or exception. The switching takes considerable time. Yet, worse, on some CPU architectures, the switching also triggers a full TLB flush. TLB, to remind you, is Translation Look Aside Buffer, which is a cache for virtual address translations. and flushing the TLB causes TLB misses and induces considerable overhead. Can we do better? Well, our insight is that 32-bit applications that run on 64-bit architectures, what is known in Intel terminology compatibility mode, are safe. The reason for that is that all the registers that can be used to reference memory are 32-bit long and masked by the hardware. Therefore, user space code can only reference user space data and cannot access, even speculatively, the kernel space. Our solution is therefore to turn off page table isolation for 32-bit applications. Yet applications, even if they rarely do so, can switch between 32-bit and 64-bit modes. We therefore trap switches between these modes and turn on PTI if such a switch occurs. Our solution has advantages, but also some limitations. The two nice properties of our solution is that it eliminates the PTI overhead, and in addition is transparent, excluding a small limitation that has no impact on real workloads. The benefit is even greater on old machines that do not support what is called address space IDs, a feature that enables the CPU to cache address translations of both the user and the kernel page tables at the same time. On these machines that do not support the feature, each system call causes a full TLB flush, and therefore these machines experience many more TLB misses. In addition, our solution is very beneficial for virtual machines where each TLB miss is more expensive as each virtual address of the virtual machine goes through two translations. But admittedly, this solution has several limitations. There is an Intel CPU feature that is called SMAP, which prevents malicious or erroneous execution of user space code by the kernel. PTI can emulate this feature for all CPUs, so removing it prevents this protection. Yet this protection is unrelated to Meltdown. The other limitations are a result of using 32-bit mode. Applications can only address 32-bit and therefore have a limit of 4 GB of memory. In addition, in certain cases, applications run slower on 32-bit. They do not utilize the full 64-bit registers width, and they cannot take advantage of RIP addressing, an addressing mode which improves performance for position-independent code that is only available in 64-bit mode. So let's have a look on the results. We implemented our solution on Linux 4.15 and ran benchmarks on 4 CPU generations, with and without virtualization. We compared 3 setups: PTI, using page table isolation; unsafe, which runs without PTI, and we only use it as a reference for optimum, or what we had before Meltdown. And finally, we have Shrink, our solution, running a 32-bit workload equivalent to the previous ones, but using our patched kernel. Note that all workloads were executed on 64-bit kernel, and we use Docker to simplify deployment. Let's start with the simplest micro benchmark. This figure shows the normalized latency of a very short system call, getPID, relatively to a kernel with enabled PTI. The purple line, which is the baseline, therefore shows the latency with PTI. The green-white bar shows the performance without page table isolation, and the blue bar shows the performance of our solution. The left chart shows native latency, and the right one shows latency of workloads that run in a virtual machine. The different clusters show performance for different CPU architectures, the oldest on the left, the newest on the right. As shown, Nehalem, that does not support address space IDs, has many TLB misses with PTI and correspondingly has the greatest overhead due to PTI. Yet regardless, all of the CPUs exhibit slowdown of over 3x with PTI relatively to what we had before that. Our solution reduces these overheads to no more than 50%. As shown in virtual machines, PTI can cause 10x slowdown, but does not cause further slowdown in our solution. Other workloads, such as get operations on Redis, a key value store, exhibit the same behavior. Here we show the normalized throughput, so the higher the better. PTI, as we can see, causes overheads of over 50%. Shrink, our solution in contrast, has negligible impact and interestingly, in certain cases, has slightly better performance than the unsafe setup. Similarly to Redis GET requests, Nginx, a popular web server, also shows considerable throughput improvement relatively to PTI, which is up to 30% natively and 40% on virtual machines. Yet we see no apparent benefit on native machines that do support address space IDs. So we saw that using our approach can improve performance, but this is not always the case. If your code has few system calls and benefits from wide registers and RIP relative addressing, our proposed solution performs worse. This figure shows the performance of Redis L-range queries, and we can see that our solution performs 20% worse than PTI. To conclude, we show that 32-bit applications on 64-bit setups do not require PTI. With small changes to the operating systems, we can disable and enable PTI transparently for 32-bit and 64-bit code and protect against meltdown. Consequently, 32-bit applications can run faster than their 64-bit equivalent with PTI. We tried and failed to push this feature to Linux. Many other attempts to selectively turn on and off PTI failed as well. If we look forward, or some can consider it in hindsight, we can say that adding security hardening mechanisms that are based on operating system behavior can prevent vulnerabilities such as meltdown. We know that operating systems use the lower half of the address space for user space code and data. So in this case, a simple feature that allowed to mask user space addresses in a similar fashion to 32-bit masking would have prevented meltdown.
Thank you. That was a very interesting talk. And while we wait for questions from the audience, I have one question. So could you share the reason why the patch was not accepted in the Linux kernel?
Yes, I think there were two reasons. One reason is a general reason. There were many attempts to say, and Windows, as far as I know, does something similar, to say, here is a trusted process. I want this process not to have PTI. And all of those approaches were really declined, pushed back. We said something a bit different. We said, here is something that is safe for sure. But the concern was that safety is hard to measure. Once the concern was that if, and that's what Linus Torvald said, if we make a mistake, I think we didn't, but that's I'm biased. If we made a mistake, nobody will notice it, and the security will be broken, and only the malicious people or the other security researchers might notice it. So this is a problem. I'm not sure it's this argument really holds, and please stop me if there are other questions, because we noticed on a different security vulnerability on Spectre that there was a situation in which security is broken if you have one indirect branch in the kernel. And there was a lot of effort on preventing it, but eventually in certain setups, you did have indirect branches in the kernel and nobody noticed. So it's, this argument is true, but it's not that we broke this theory, if it's clear, it's we are not worse than the others.
Indeed, yeah. And so do you have any thoughts on, how you can try to demonstrate better security of the solution in the sense that it does actually prevent leaks? I guess the arguments again apply to other proposed solutions as well as to how do you validate their security. So do you have any comments on that?
Yes, so I have two things to say. First of all, maybe this solution, would have been more useful for a different operating system like Windows that has a lot of legacy code that is written in 32-bit and not recompiled similarly to Linux. When it comes to the security aspect, basically, I think that some auditing is missing. There are many attempts, for instance, in the Linux kernel, to check that there is, for instance, no mappings that are both readable and executable, writable and executable at the same time. All kind of those things exist, but maybe not to a sufficient extent. Maybe those needs to be extended to ensure that any security mechanism that is supposed to prevent attacks is really doing what it's supposed to do. So some auditing, in a sense, is not auditing, some further assertions are needed.
Right, sure. Okay, so I have one more question. So this talk was about how to apply mitigations for 32-bit applications, right? And so it's a pretty interesting idea. So I was wondering, like, if you could apply a similar idea even with 64-bit applications, why just applying masking. I think that's what you were alluding to towards the end of your talk, by masking the address space and restricting it to a certain range, right? So I think you were saying that there is some need to provide support from the CPUs to do that masking, but in the absence of that kind of feature, can you do something just from the software at this point?
So probably I wasn't clear enough and I should have clarified it because of the short time, but basically you do want masking, but not just masking. You want the masking to be done without any speculation in the way, because you do have all kinds of translations through the paging, but you want to prevent any speculation on the way. And other features, like a feature which is about to be deprecated, which is called MPX, also allow you to do some kind of a masking. But the problem is that those maskings, not exactly masking, like raising an exception if something goes wrong, those events happen later in the pipeline and more in a speculative way. So we need something very simple, but very early, because if it's complicated, it will make the system, slow. We want something very simple. And segmentation, in a way, also there was a study about 32-bit, that segmentation inside 32-bit operating systems can also be used to prevent a meltdown attacks. So the masking needs to be done very simply, but very early in hardware.
Sure, great. Okay, thank you very much. This was a really very interesting presentation and the discussion.